let's start with this idea of momentum. I think impulse maybe may not be as common knowledge, but I think momentum is something that we talk about colloquially in everyday speech or settings, right? So how would you describe momentum? What is it? The hand motion. That's
The continued motion of an object.
Say again?
The continued motion of an object.
Continued motion of an object?
Yeah, kind of the tendency of an object to remain in motion. Same thing.
Okay, so kind of synonymous with inertia, maybe. What else? I'm really looking for not a technical explanation of momentum, a really colloquial explanation.
What is colloquial?
Colloquial means kind of everyday conversation, standard conversation, not technical. Sure. Speed. Okay, so maybe related to speed. So the faster something goes, the more momentum it has. But I mean, it's got to be more than just speed, right? Because if I throw a sweet pea at you really fast, it probably doesn't have a lot of momentum. Right? Something else. If it was frozen, maybe it hurts a little more. I don't know. But, or if I ball up a piece of paper and throw it away. So maybe more than just speed, right?
The energy of an object?
Energy. Okay, so if we talk colloquially about energy, usually, well, now we're getting in a rabbit hole, because then I'm going to ask you what energy is. Yeah, how would you describe energy? But let's stick with momentum.
It's also related to mass.
Okay, so related to mass. So that's how we're going to tie in inertia, right? Because we describe inertia not as a very qualitative thing, but the way we measure inertia is usually mass. So the more mass it has, and also the more velocity it has, the more momentum it has. How about a scenario? Someone give me a scenario where you would use the word momentum.
If you're running and you can't stop.
Okay, so you're running, you can't stop. Fantastic. What's that? Anything else?
The Cubs had momentum.
Skiing down the hill and
The Cubs had momentum.
the Cubs have momentum. Okay, so no, I think that's actually a really fantastic example, because what is implied in the statement that the Cubs have had momentum going into Game 7 is that they seemed unstoppable. They seemed difficult to change course, right? So when we talk about inertia and we talk about momentum, that's kind of part of it, right? Is the ability to affect the current motion of something. So if you say something has a lot of momentum, right? You might include, a train that is very massive but going very slowly still has more momentum than a fly that is flying really fast, right? Because the train will seem much more difficult to move than a fly where you're slow, right? So I think especially for momentum is a very kind of a visual thing sometimes, and so it's good to have that kind of gut everyday experience definition of momentum. So we'll get into kind of a mathematical definition of momentum now, but keep that in mind, right? Your everyday experience of momentum. Okay, so I'm going to put two equations here, and this is how we're going to relate momentum. We have Newton's second law, right? And in this case, we're just going to look at a situation where you have just an object experiencing one singular force. So let's say you have a satellite out in deep, deep space, no gravity, nothing else, and it turns on the thrusters and it just goes. Right? So we can have a very simplistic scenario here. And as it accelerates, if we use our kinematics, assuming that is constant acceleration, we would get something like this for the velocity. Right? I just go in line with things we already know. If it has some constant acceleration. If we were to graph these motions, do you have something to turn in, Rachel? Test. Oh, yes. Shoot. Give me 1 second when you have a seat. I'm going to pause for a second. I need to take, I forgot I had to give her a thing. So give me 1 second. Do you have your Chromebook?
Oh yeah, such a help. You want them?
Okay, sorry about that. Let's go ahead and continue. Okay. All right. We gotta move on. Okay. So, constant acceleration, right? So, if we look at the graphs, okay, of how we determine this equation, we had two graphs. We were concerned with a acceleration versus time graph, and alongside that, we looked at and that's a t. We looked at a velocity versus time graph. And so if it's constant acceleration, right, this is going to be flat because it's constant. And one of the important things that we established was that your acceleration is a measure of the slope of your velocity, right? And this is really actually a definition for acceleration. Your acceleration is defined as the rate of change of your velocity, right? dv dt. In this unit, we're going to be incorporating a little more of the calculus. And again, you don't need to actually make any calculations with it. You just need to understand the language, the terminology, and how it's written, the meaning behind it, right? So compare the calculus version to the non-calculus version. The non-calculus version allows us to determine kind of average accelerations and based on net changes in velocity and net changes in time. But when you look at what's that? When you use the derivative, that allows you to look at an instantaneous moment, right? What is the acceleration at that particular moment? Now, in this case, we're using a pretty straightforward scenario. It's constant acceleration, so this is constant, and so that means your slope is just some number and it's constant, right? So you might have a velocity graph that looks like this. And it starts at some initial velocity, and it ends up at some other velocity later in some period of time, right? And so this slope will be A. Okay. And so we say that the derivative of the velocity versus time graph, which is the slope, is constant, so that the acceleration versus time graph here is flat. And if we want to go backwards, from here we can kind of see that as you pass in time, the amount that your velocity changes, this dv, or this delta v, how much your velocity changes, is essentially just the area under this graph. Right, so after some amount of time, this is your change in velocity. Right. And so this was in the video I posted a little while ago. It's also in your book. You know, this is basic kinematics. And so from here, we can say that your change in velocity is equal to AT. Very specifically for constant acceleration, right? Base times height, that is the area, that's delta V equals to AT. So based on what you're seeing here, okay, how can I relate a force into my kinematics? What do I have to change here to now make this a matter of force instead of just a matter of acceleration? Akash. Add a mass value, multiply by a mass value maybe. So I will multiply by mass on both sides. And voila, my mat turns into a foot. I'm just kidding. This is F times T, force times time equals to mass times delta V. So this should make sense. Again, step back and really try and understand at a very, what's that? Try and understand the meaning behind it, right? If you apply a force on an object for a certain amount of time, that results in a velocity change scaled by the mass. That should make sense because before, when we did kinematics, we had accelerations just magically. Things just had an acceleration, right? We just said it accelerated at 2 meters per square second. We never really looked into how it was being accelerated. And now with Newton's laws under our belt, we can say, okay, well, you have these forces acting on it. And the forces are what causes it to accelerate. And it'll accelerate depending on the mass. And so on the other side of the equation, when you talk about acceleration, you also have change of velocity. So now it's this mv instead of just v. So it is, well, okay. So if this is kind of how the equations work out, let's look at the calculus side of things. We said that the way you represent this area under the curve through calculus is we would call it the integral. The integral of this acceleration function with respect to time gives us our change in velocity. Okay? And really trying to understand what the difference between this and the non-calculus version. The non-calculus version would be that if I take my average acceleration and multiply it by some change in time, I can get a change in velocity. This is looking at a scenario where your acceleration is not averaged. It could be increasing and decreasing and changing in all sorts of ways, such that what the dt means, if in here dt is to chop it up into a really small slice and look at the slope at that very particular moment, what this dt means is to do the same thing. You're taking a very small slice in time, but you're looking at the area of that rectangle in that very small slice in time. And then you do another slice, and you do another slice, and you do another slice. And you add up all these slices. Okay? And eventually you'll find that that's essentially what a Riemann sum is. A Riemann sum is you take a graph that can be of all kinds of shapes, and you make all these approximations of mini rectangles underneath the graph that have a height of the graph at a particular point and a really small thickness, and then you use calculus to say take the limit as the thickness of the graph goes to 0. Then you add them all up. So you're effectively adding up an infinite number of infinitesimally thin slices, and that's what the integral does. Okay, so just be mindful about the meaning of the how I'm writing it out. The dt means we're taking slices of time. This integral symbol means to add them all up. Without the integral symbol, you're not adding anything up. And the dt is just looking at slices of time. Okay. All right. So if this gives us the calculus definition of velocity to acceleration, then therefore, what would the integral equation for this one look like? Now that I have force in there. The integral of what? Okay, integral of ma dt will now equal to m delta v. One thing that's really important in this assumption is that your mass cannot be a function of time. Well, actually, no, I take that back. You can totally have mass as a function of time because it's inside the integral. You can't take it outside of the integral unless it is not a function of time. So you can definitely have, yeah, you can do all that. So actually, then we can say this is your force times this dt is equal to mass times delta v.
Don't you have to integrate the right side too because there's no mass? Yes, you should have the integral of mass.
Um,
You can pull that.
well, no, if it, I guess,
You have to integrate the right side.
Hold on, let me think about that.
Because time is a function.
If mass is a function of time, then yeah, then you'll have something to deal. So actually, yeah, I guess you have to have mass as a constant. So you can't have changing mass here. Well, you know what? For now, we'll come back to that. There's actually a way you can get around that. So as we establish kind of the foundations, let's just keep it simple, and then you'll see how it works out. So actually, what I want to do then is let me actually write it like this. I'm gonna write it like this. You're gonna have mv minus mv naught. So I'm just taking the difference in velocity, and I'm actually grouping them into two parts: your final mv and your initial mv. So this mv, this is what we call momentum. Okay, they're both momentum. You can kind of think of it as like an initial momentum and a final momentum. Okay, so when we look at momentum, momentum is a property of the object. It's kind of the state of the object. Okay, so if you can describe an object as having a certain acceleration, a certain velocity, a certain position, in the same way you can say it has a certain momentum. Okay, so what the symbol we use is P. P is for momentum. Lowercase p, not uppercase p. Uppercase p we'll use later for power. Okay,
Wait, why isn't the initial momentum?
is final minus initial, because it is the change. No, just mv is momentum, or just p. Just p or just mv.
Why is it MV and not MV initial? Like, it's the force that it already.
Either one, they're both momentum. So you can describe this as p minus p initial.
Okay.
Okay, they're both momentum.
So basically, mass times
Just
velocity.
mass times velocity is what we will call momentum. On the left-hand side, okay, this is mv is like a property. This is kind of a calculation. This is what we call impulse, and we use J. J for impulse, P for momentum.
So impulse is equal to momentum.
Not quite. The change in momentum.
Oh, yeah.
So an object that is going straight and level can have a certain momentum, and when a force is applied to it over a certain amount of time, its momentum will change, and how much it changes by is the impulse. Okay, so you can measure it two ways. You can describe the impulse as how much the momentum changed, or you can describe the impulse as how much time was spent pushing on it with a certain amount of force. Okay, so they're the same thing, or they represent the same thing. They're equal. Okay, now this is just kind of definition stuff, and frankly, there's no new physics in this. This is all based off Newton's second law, right? We just use Newton's second law and just the definitions of acceleration and velocity, and we're just looking at constant acceleration. But you can kind of see how from here, I know earlier I said that your mass can't really be a function of time, but if you look at momentum, if you really don't describe mass and velocity separately, but if you can describe momentum as a function, right, which includes both mass and velocity together, you could have a variable like a momentum that is a function of time. Okay, this determines how your momentum changes, right? No matter what the function is. This just is the net change in momentum. Or you can create a function for it. Right? This can create a function for how your momentum changes with time. Okay, so what would the graph of this look like? How do we represent this graph graphically? Well, let's take a look. If I want to represent this part graphically, I can create my force versus time graph. Okay, so if I do a force versus time graph, if I have a constant force, then the area under this graph represents my change in momentum. Okay, that's how they're related, at least graphically.
that also impulse?
Yes. Yeah. So that is kind of worth mentioning. You know, it's the change in momentum. You can't know what the initial momentum is, or what the, you can only know how it changed. One other thing that's worth noting is that momentum is relative. It's not intrinsic the way mass is intrinsic. Momentum is dependent on the velocity, but velocity is dependent on your reference frame. So if I'm in a car that's going 60 miles an hour down the freeway and another car right next to me is driving right next to me, also going 60 miles an hour, relative to me, it has no momentum because we are, in essence, stationary with respect to each other. If there was no, if we were, okay, maybe not, don't think of the road, but if you were two satellites in deep space and it was just black everywhere and you could not have any reference for how fast you're moving at all, and that satellite was flying along with you, and you could not really have any other reference for the fact that you're moving, you wouldn't be able to tell it has any momentum. Okay? So momentum is relative. That's really important. That's at least up until you start getting to the speed of light. Okay, so when you start approaching the speed of light, things behave very differently. Everything that we're doing in this class is classical mechanics, which means that Einstein didn't exist yet, and all relativity didn't exist yet, and so anything that goes really fast, you can't do any of this, or you have to modify this. Or if things are extremely small, the size of protons and neutrons, then this is also very different. Electrons don't, quite behave this way. So, but everything else in between, which is a lot, you can do this. Okay. So this actually means that there's actually also a kind of deeper meaning in this, which can go to show that F equals ma is actually a simplification. Because when we do F equals ma, what we really mean is maybe m dv dt. But like we said, that's not really actually the complete picture, because it's not a matter of velocity that the force is influencing. It's the momentum that the force is influencing. It is when you push and pull on something, its ability to change its motion is not so much a matter of just mass or velocity separately, but together, right? Together. So actually, it's kind of better to write it like this. Right? You're really looking at the rate of change of momentum. That is actually the original meaning of Newton's second law. But you don't usually see it because it kind of requires some depth of study with physics before anyone can really understand it. And F equals ma is kind of the easier one to memorize, I think. But this is actually a better definition of what a force really does. A force changes the momentum of an object. And this is a better use too, because later we'll see that the law of conservation of momentum, maybe you've heard of it, is actually just a restatement of Newton's third law. And we'll see why in a minute. Okay, so what that means is that we can actually make another graph then. We can graph a momentum versus time graph. And so that if there is a constant force being applied on an object, then the slope of it is the force. So just as there is a kind of back and forth between acceleration and velocity, if you multiply both of these by m, this is ma, that's mv. This is essentially force, that is essentially momentum. So you have a flat force graph and a linear momentum graph, right? That's how they're related. So slope of this gives that, the area of this gives that. Or sorry, I should say that the area of this gives you the change, not necessarily the full thing. You always have the plus c. Okay. Any questions about what impulse is, what momentum is? Mathematically, I think they're pretty straightforward. One last thing to point out about momentum and impulse is that they're vectors. Because force is a vector, means it has direction in addition to magnitude. It means that if you're pushing this way and the momentum was this way, its momentum change in the other direction. If you go from 5 Newton seconds this way to 5 Newton seconds that way, you had a 10 Newton second change in momentum. Your direction actually matters. So your force is a vector, which means that your velocity change is a vector, which means momentum is a vector, and that also means impulse is a vector. They're all vectors. Okay, they all have directions, which means that just the same way we handle vectors in kinematics and Newton's laws, when you have a 2-dimensional or 3-dimensional problem, you'll want to break it down into its components. Okay, so you can talk about the momentum in the x direction, and the momentum in the y direction, and the momentum in the z direction, based on the forces in the x and the forces in the y, so on and so forth. Right? You break it down into its parts or components. A quick note about the units. So if it's MB, you have kilograms meters per second. But more commonly, if you look at this is Newtons times seconds. More commonly, you'll see Newton seconds. There's no shortened form of this. And it's not a joule. A joule is different. A joule is a Newton meter. We'll get to energy later on. This is just Newton second. There's no shorthand for this. What's that? A Newton second is the more common one. But if you see kilogram meter per second, that's also a legitimate unit for momentum.
That's for momentum and impulse, or
Well, you tell me.
yes.
Yes, because they're equal. Yeah.
So look at the graph on the bottom left. Impulse is equal to force times time, right? Or like minus p initial.
So if you're looking at this graph and you're trying to determine what impulse is this. If you change, this is J. If you have a change in momentum, that is your impulse.
So momentum means the same thing, like colloquially in physics, but impulse means a different thing?
So impulse is your change in momentum. So if you imagine a baseball flying at you, it has a certain momentum to it. That means it has a certain oomph and speed and mass and whatever. And then if I hit it with a baseball bat, I apply an impulse to it, which then results in the momentum being that way now. Okay, so an impulse is like an action. You do something, you do an impulse, just the same way you apply a force, you push on something. It is an action not intrinsic in the object, as opposed to momentum, which is like a mass of velocity and acceleration. It's describing the object itself. Okay. So we're done. I mean, that's chapter 9. Understand? So that's pretty much it, though. To be honest, this is the main idea of this. But I think you'll see, just like in the Newton's laws, the laws themselves are simple. The rules are simple, but the scenarios can make it kind of tricky. Okay. So let's look at an example real quick. Let's look at a pretty straightforward example. Let's say you have a person and they are trying to juggle a soccer ball that is falling down onto his foot.
Same.
Okay. So the soccer ball falls down onto the foot and then they bump it up and then it goes up. So let's say it is half a kilogram and it falls at 5 meters per second and then it gets bumped up 5 meters per second. Okay, so I know that's kind of hard to tell what I'm writing, but it's like going down at 5 meters per second and then it goes up. Okay. And what I want to know is, what is the impulse J? No.
30.
It is not just the velocity change, right? Momentum is more than just velocity change. Well, let's go ahead and just kind of walk through this one together anyway. And then the next couple examples, I'll have you guys give it a try. So
So there was no impulse?
there is impulse. There's definitely an impulse. So you gotta be very careful because even though it's 5 down and then 5 up, the direction is changing. Because the direction is changing, that's where the vector part comes in. So when you talk about impulse and you talk about momentum, like all other vectors, you have to have some sort of reference or choice of what's positive, what's negative. So let's say up is positive. That means that the initial momentum is half a kilogram times a negative 5 meters per second. And so therefore it was a negative 2.5 Newton seconds. Okay. And then afterwards, after it is kicked upward, whoops, there should be nothing here. The final, ignore this. The final momentum will be half a kilogram times 5 meters per second, which is 2.5 Newton seconds. Okay. And if you want the impulse is the change in momentum, which is the initial, or sorry, the final minus the initial. So that will be 2.5 Newton seconds minus a negative 2.5 Newton seconds, which equals to 5 Newton seconds. Right? So just be very mindful about that. Direction changes require a force. They require an impulse, a change in momentum. This can get particularly tricky if it comes in at an angle. Okay, you want to really keep track of the components, right? If the soccer ball came down at an angle and then reflected at a certain angle, it is only the perpendicular component that's actually changing, but maybe it still has the same momentum in one direction. Right? So just keep an eye out. Any questions on calculating momentum or impulse?
The perpendicular component?
If it came in like at an angle, don't worry about it.
Okay.
We'll get to it. We'll get to it. All right. So in this process, as the soccer ball is actually hitting the foot, if you were to actually graph that interaction, in real life, right? In real life, it is unlikely for that interaction to look like this. That'd be kind of weird, because your foot doesn't instantly apply the force and apply a constant force and then suddenly disappear, right? That's just not how objects in real life interact. More likely, it is as the ball comes in contact with the foot, the ball starts to compress. As it compresses, the pressure forces on the inside push back on the foot and as it expands, increases the force, and then as it starts to leave contact with the foot, you lose any kind of force, right? And so there may not be really a good function that represents this, or maybe there is a way you can gather this information experimentally. You have some sort of force sensor or pressure sensor on the foot, and it gives you a bunch of data, and you plot it all out, right? And so, again, the idea is if you know what the force looks like at every moment in time, you can figure out what the net change in the velocity is going to be. And that is the area under this curve. Okay? This area will give you J. Now, sometimes you may be asked to find like the average force. And again, that kind of is looking at the calculus and putting it all together, I don't remember exactly if this is right, but I think it's the fundamental rule of law of calculus or rule of calculus, which is that for every continuous function, you can find an average derivative or average slope between. Is that the mean value theorem or something like
Yeah.
something like that? And so that means that you can find some sort of average force times the total time that's here, and there must exist some average value here as long as it is a continuous function. Whatever, continuous and differentiable, something like that.
Yeah.
Good old calc. And so that will equal your change in momentum. And so when you look at this, the kind of problems that you'll see, it just comes down to how they want to make you do algebraic manipulation. Maybe they want you to find average force. Maybe they give you the average force and they ask you how much time is the foot in contact with the ball. Maybe they give you both of those and they say, okay, now what is the final momentum, or what's the initial momentum, or what's the impulse? It's just that's how the questions are going to be. But as long as you understand this connection between all of them, then you're good. Okay. Questions on this? Okay. Now let's actually look at two specific kinds of interactions. That is collisions and explosions. So we're going to look at collisions first. Okay. When we talk about a collision, that has a very specific meaning behind it. I know it may seem super obvious, but a collision means you have two separate entities, two separate objects that come together, contact, apply forces, interact with each other, and either they separate with different velocities afterwards, or they stick together and they stay together. And we're going to look at the sticking together one first. That is, in the book, they call it a perfectly inelastic collision. So when you think of elasticity as being bouncy, then inelastic means there's no bounce. They just stick. Okay, so perfectly inelastic collision. What I've noticed on the college board or AP exams is they don't always include the word perfectly. They just say it's an inelastic collision, but they mean the same thing. It's either inelastic, they stick together and they don't come apart, or it's elastic, they touch each other and they come apart. Right? You can't have a somewhat inelastic collision. It's where they kind of come together but don't come apart, but then come. I don't know. If it's inelastic, that means they stick together. More often, they'll actually have either inelastic, they stick together, or elastic, they hit each other, they come apart, but the interaction involves energy loss. Or lastly, you have perfectly elastic, means you have a perfect collision, there's no energy loss whatsoever, but we'll explore those when we get to energy later. For now, let's just say inelastic means they stick together, elastic, they don't stick together. That's it. Okay, so let's just, for example, say you have like a potato, and you're going to shoot it with a potato gun into a canister. Okay, you shoot the potato into a canister. This has a certain mass in it with a certain velocity. I'm actually going to say this is the initial velocity v0, comma 1. Okay, so I know the notation can be kind of confusing, but this is the initial velocity of object 1. Okay, and then this is the can, this is object 2, it has a certain mass. I guess you could use A and B instead of, or P and C for potato and can, whatever. Up to you. And so before the collision, they're separate, and then the can is stationary, and then after the collision, the potato is inside the canister, and they're moving together. Okay? So that is what an inelastic collision might look like. Has anyone in here not taken the test yet? Okay. Then I will not use test questions as examples. Moving on. So here's the thing. This potato has some momentum to it. And when it runs into the can, it is pushing on the can. The can gains momentum. If the potato pushes on the can, what is the momentum change going to be for the potato? How can we determine that?
Slow down.
It'll slow down, but by how much, relatively speaking?
Looking at the mass of the can, question mark, and the force the can exerts on the potato.
Okay, so all right. Let's get some hands. So Hia said it should be depend on the mass of the can, the velocity of the can,
M1
velocity, and things like that. Okay, you guys are thinking very mathematically.
Is there friction on the ground? Is there
No friction. So let's just say this is just kind of floating there, just in space. Space is space potato, space can. Okay. All right. So I guess I guess what I'm asking for is a little vague, but if this potato gives this can a certain amount of momentum, what is the change in the potato, the momentum of the potato? Is it going to be the same? Same force, right? In the opposite direction. Perfect. From Newton's third law, whatever force the potato applies to the can must apply back onto the potato. That is this part, right? If this is the momentum that is being gained by the can because there's a force being applied to it over time, at any moment, the force that's being applied to the can must also be being applied to the potato in the other direction, which then therefore means that this curve must be exactly the same for the potato in the other direction. That's what Newton's third law says. So therefore, if the potato has the exact same curve in the negative direction, it must lose the exact same amount of momentum. So whatever momentum the can gains, the potato must lose that much momentum. That really is why the law of conservation of momentum is true. It's really just based on Newton's third law. Okay. I have actually seen that kind of multiple choice conceptual question before, where it asks the conservation of momentum is a restatement of which law, and then that really is, it's the third law, the equal and opposite reaction. That's why it's conserved. Okay, so when we write it out, the law of conservation of momentum, you have, in the absence of external forces, and that's important, and we'll take a look at what external forces really means. In the absence of them, though, a system will conserve its momentum. In other words, what's meant by it'll conserve its momentum means its momentum of the system will stay the same. So the potato's momentum is not going to stay the same. The can's momentum is not going to stay the same. But when you put them together as a system, as a whole, together, there's nothing else acting on them. And so therefore, their momentum should be constant. Okay? So if you were to write it out mathematically, the sum of the momentums is equal to the initial momentum, which will equal to the final momentum. And so from here, you can calculate whatever relationship you need based on whatever numbers they give you. If they give you the masses and the initial velocity, you can find the final velocity. If they give you the final velocity, you can figure out what the mass of the can had to be, or something like that. There's all sorts of whatever algebraic manipulation you need to do to get the answer that you need. Okay, so for the sake of time, last time I gave one problem at a time, but let's go ahead and do two kinds of problems here at the same time. So I'm just going to put two up here. One is an example of a collision. Okay, so let's say, for example, you have one blob of silly putty shot down at another blob of silly putty, and afterwards they collide. Blam. Okay. And now you have a bigger blob of silly putty. You have an inelastic collision. Now, sometimes on the kind of problems that you'll see, it will not tell you explicitly that is an inelastic collision. But if I tell you that a truck runs into a car and they slide off together, that's how you know it's an inelastic collision, because you have two objects becoming, ending up as one kind of moving together. Or if you have like a jet flying and landing on a aircraft carrier, and it lands, that is an inelastic collision. Sometimes collisions don't have to be, something hitting something else. If you looked at an aircraft carrier and the airplane as a system, together they have some amount of momentum. As the airplane lands, it must slow down by the friction of the tires. So if it is slowing down, it is pushing the carrier forward a little bit. And so then their momentums combine, and then if the plane is parked on the carrier, then it's like a collision. It's like an inelastic collision. Right? So, all right. So let's say that this is 2 kilograms, and this is going at 2 meters per second, and this is 3 kilograms, and this is going at 5 meters per second. I want you to determine in vector form, okay? Vector form meaning I want to see I and J kind of notation. So let's say that this is 2 meters per second in the I, and this is 5 meters per second in the J, downward, or so actually negative, okay? No. If I just do everything as 1, it's silly. Okay, so I'm just going to vary the numbers. Okay, so what is this going to be? Okay, so here's an example of a collision. Another kind of problem sometimes we deal with are explosions. So an explosion is the reverse. Instead of 2 objects coming together to become 1, you have 1 object splitting up to become 2 or 3 or whatever, right? So let's say, for example, you have a potato, and it is just resting in space, okay? A at rest space potato. And for whatever reason, spontaneous combustion, yeah, French fries. Explodes, you have pieces.
But if it's spontaneous, then it would have happened. If it's spontaneous, that happens naturally. Are we not talking chemistry terms?
Sure, it can happen spontaneously. I don't know. Frankly, it doesn't matter, actually. As long as everything is contained with the system and it was initially at rest. Then let's say this is launched out at 3 meters per second, and this is 1 kilogram. This is launched up this way, and this is in the I. This is 0.5 kilograms going at 2 meters per second in the J. And then I want you to determine this. Okay, so two problems. Okay. When they collide together and combine, how do you get the final velocity? When they explode and come apart, how do you get the velocity? Vector form. So something I plus something J.
What is the weight of the potato at the beginning?
It is 3 kilograms. Oh, did I not write that? Sorry. 3 kilograms. Sorry. Three.
Is that the magnitude
No, I want it in
Velocity.
vector form of the velocity.
Do you have the mass of the third particle of tangent?
It's 1.5 because it's.
Oh, there's 3. Oh, yeah,
I don't get what the second question is. Can you explain it to me?
So how do you figure out how fast this third piece is going after explosion?
Okay, so it's equal in all directions. And
Well, when you say it's equal in all directions, what's equal in all directions?
the amount of force applied.
Not necessarily.
The initial momentum.
Only that the initial momentum of this whole thing must equal the final momentum of the whole thing, which is all 0.
So there was no force applied, so your force can't be equal because there was no force. It was just.
The only reason why I say the force is not equal in all directions is there's a force sideways on this one, but a force diagonally on this one, and a force upward on that one. So they're, you know, component-wise, yes.
Yeah.
Component-wise, of course. It is, yeah, 2 and 3, and then this will be 5. Guys, okay?
Yeah, I don't know if you have time, but I just don't know how to like write in
Write it in
vector
vector form?
notation, yeah.
Let's go ahead and do one of them together, and then you can kind of check your answer. So, when you're doing these, you want to split the momentum up. You know, some of the momentums in the x, kind of like that. Some of the momentums in the y, right? Kind of like we do some of the forces, or and so. When you look at the momentums in the x, you have 4 Newton seconds going to the right in the I direction, and that has to equal to the x momentum after the collision. So this will be 5 kilograms times whatever the velocity is in the x. Right? This is the initial from here, 2 times 2, mass times velocity. That will equal to whatever the mass of this is in the x direction. Sorry, the mass of it times the velocity in the x direction. And so then you get the velocity in the x direction will have to be 4/5 meters per second in the I. Yeah, because that's I. Okay, and then you do it in the y direction, you have negative 15 Newton seconds. You have negative 15 Newton seconds in the j. That's also equal to 5 kilograms. But now it's times v in the y.
Why is it negative 15 again?
Because it's going downwards. If I choose, yeah, up and right. And so then Vy will equal to negative 3 meters per second J. So when you do the notation, it's literally 4/5 I minus 3J meters per second. That is vector notation. Sometimes in mastering physics, it will ask you for the magnitude and the direction by angle. So you would have to do Pythagorean's theorem on it and find an angle relative to horizontal or whatever it is for some. Something like that. All right, that is the essence of momentum. Yeah, honestly, I think it's pretty short. Well, where momentum's going to get particularly tricky is after we do energy. There are a lot of problems that are both energy and momentum together, so that's where we're going to need more.
Could you give
I
that
guess.
the last explanation of the explosion one also?
The explosion one should be, let's see, so the mass of this is 1.5 kilograms. So in the x direction, you should have negative 2I, because it's 3 divided by 1.5. And then you have a momentum of 1 divided by 1.5, so that's like 2/3. Because the momentum of this 2 times 1/2 is 1, and then 1 divided by the mass of this. 1 divided by 1.5 is 2/3.
That's exactly what I got.
It's a good thing. All right. That is it.